Walk through the Alps today and you will find wooden structures that have stood for 800 years. Barns built in the year 1200, churches from 1100, mountain farmhouses that have endured 700 brutal winters. The wood shows no major splitting, no catastrophic cracks, no structural failure, despite facing conditions that would destroy modern lumber in a single season. Now look at your deck, built 3 years ago, with treated lumber from a major supplier. The boards are already splitting along the grain. Cracks run from end to end. Some pieces have warped so severely they pulled away from the joists. One winter of freeze-thaw cycles in Colorado or Minnesota can turn brand new decking into splintered wreckage. What did Alpine builders know that we have forgotten? How did medieval carpenters select, treat and assemble wood that would last 8 centuries in -40-degree winters, while modern pressure-treated lumber fails in year 1? The answer lies in techniques so specific, so carefully refined over generations, that losing them has cost us centuries of durability. And the most shocking part is this: the science proves medieval methods work better than modern industrial processes. Section 1. What Alpine builders understood about wood selection. Medieval Alpine carpenters did not walk into a forest and cut down any tree. They understood that altitude, species and timing determined whether wood would survive or fail, and their selection criteria were brutally specific. Alpine builders harvested larch exclusively from elevations above 1,000 meters, not 900 meters, not lowland valleys, above 1,000 meters where harsh conditions forced the tree into survival mode. At high altitude, the growing season is short, maybe 90 days compared to 180 days in valleys below. This means the tree produces narrow annual rings, dense wood, tight grain structure, where cells pack together with minimal airspace. A study published in the journal Holzforschung examined European larch from the western Italian Alps and found that Alpine larch exhibits significantly higher density and natural durability compared to lowland specimens. The researchers documented that geographic origin determines decay resistance more than any other factor. Why does this matter for freeze-thaw resistance? When water penetrates wood, it enters through pores between cells. In loose-grained lowland wood, water saturates deeply. When that water freezes, it expands 9%. The pressure splits the wood from inside. Dense Alpine larch has fewer pores, tighter cell structure. Water cannot penetrate as deeply before the surface seals. Less water inside means less expansion pressure. The wood survives. Modern lumber comes from fast-growth tree farms, wide rings, loose grain, maximum volume in minimum time. This wood is biologically programmed to fail in freeze-thaw cycles. Not all larch is equal. Alpine builders specifically sought Larix decidua, European larch from the Alps, Carpathian Mountains, or Sudeten regions. They avoided larch from Scotland or lowland France. Why? The International Larch Provenance Trial of 1944 to 1945 in West Norway proved that larches from the Sudetian and Tatra areas combined superior growth with remarkable frost hardiness. These specific genetic lines evolved resistance to extreme temperature swings. Alpine larch produces resin content up to 3 times higher than lowland larch. This resin serves as natural waterproofing. It fills microchannels in the wood structure. When temperatures drop, the resin does not freeze like water. It maintains elasticity. The wood can contract without cracking. Modern lumber suppliers do not track provenance. A 2x6 labeled larch could come from anywhere. Lowland trees with minimal resin content. No frost adaptation. The label says larch. The performance says failure. Medieval carpenters had one simple test. Does the wood sink in water? If a piece of larch floated, they rejected it for exterior use. Only wood that sank passed. Why? Water has a density of 1 gram per cubic centimeter. Wood that sinks has density greater than 1. This indicates tight cell structure, high resin content, the exact properties needed for freeze-thaw resistance. Siberian larch, a close relative of Alpine larch, used in similar conditions, scores 1,100 pounds force on the Janka hardness scale. This makes it denser than many hardwoods. Modern softwood decking typically scores between 300 and 500. The difference is survival versus failure. Alpine builders were not guessing. They were applying material science 600 years before we had the equipment to measure why it worked. Section 2. The medieval drying method. Modern industry abandoned. You can buy treated lumber and build with it the same week. Medieval Alpine builders waited 3 to 7 years between cutting a tree and using the wood. This was not superstition, it was survival. Alpine carpenters cut trees only during winter, specifically between December and February, and within that window they preferred the waning moon phase. This seems like folklore until you understand wood biology. In winter, deciduous larch trees enter dormancy. Sap retreats from the trunk into the root system. The tree protects itself from freezing by removing liquid from vulnerable above-ground tissue. When carpenters cut during this period, they harvest wood with minimal moisture content and maximum concentration of protective resins. Moon phase timing relates to atmospheric pressure changes. During the waning moon, slightly lower pressure makes it easier for any remaining sap to drain from cut logs. Whether this effect is large or small, winter harvest timing is documented in medieval forestry laws across Alpine regions. It was not optional, it was legally mandated. Modern logging operates year-round for economic efficiency. Trees are cut in summer when sap is at maximum. That moisture stays in the wood. When the lumber sits in your yard and winter hits, all that trapped moisture freezes, expands and starts the splitting process from day one. Once cut, Alpine builders did not stack logs horizontally. They stood them vertically in covered but ventilated structures called stables. The logs remained in this position for 3 to 7 years. Vertical positioning allows gravity to drain residual sap downward. Any moisture that enters from rain or snow runs down and exits at the base. The wood never sits in water, never traps moisture in horizontal grain orientation. During these years, something critical happens. The resin crystallizes. When larch resin solidifies slowly over time, it penetrates throughout the wood structure. It fills cell walls. It coats the interior surfaces of pores. This creates waterproofing from inside the wood, not just on the surface. Modern kiln drying forces moisture out in weeks using heat. This is faster but fundamentally different. The rapid process does not allow resin crystallization. It actually damages cell structure through thermal stress. The wood emerges dry but weakened, vulnerable. A 3-year naturally dried Alpine larch board has resin-reinforced cell walls. A 3-week kiln-dried modern board has empty, fragile cells. Both test as dry. Only one survives. Section 3. How freeze-thaw cycles actually destroy wood. Before we can understand the Alpine solution, we need to know exactly what goes wrong. The failure mechanism is precise, measurable, and brutal. Water is unusual. Most substances contract when they freeze. Water expands. Specifically, it expands 9% in volume when it transitions from liquid to solid ice. When water enters wood pores and freezes, that 9% expansion generates enormous internal pressure. Wood cells are strong in the direction of the grain, but relatively weak perpendicular to it. The expanding ice pushes outward against cell walls. If pressure exceeds the wood's tensile strength, microfractures form. One freeze-thaw cycle creates microscopic damage. 10 cycles make that damage visible. 50 cycles, which is a typical winter in Alpine regions with daily temperature swings above and below freezing, turn microfractures into major splits. You might think pressure-treated lumber solves this problem. It does not. Here is why. Pressure treatment forces chemical preservatives into wood under pressure. These chemicals prevent rot and insect damage. They do nothing to prevent freeze-thaw splitting. In fact, the treatment process can make splitting worse. First, pressure treatment only penetrates about 6 mm below the surface. A standard deck board is 38 mm thick. That means 70% of the wood's interior remains untreated. Water that gets past the treated surface zone saturates the unprotected core. When that core freezes, the board splits from inside. Second, chemical preservatives make wood more rigid. They reduce natural flexibility. When winter contraction occurs, treated wood cannot flex slightly to accommodate the stress. It cracks. A scientific study in the journal Construction and Building Materials tested freeze-thaw cycles on European larch versus Norway spruce. The larch wood exhibited 64 to 80% higher resistance. The reason? Higher density. the exact property Alpine builders selected for 800 years ago. Watch where deck boards crack. Almost always, the splits begin at the ends of the board. Why? End grain is exposed wood cells viewed from the side. Imagine looking at a bundle of straws from the end. Each straw is open. Water rushes into these open tubes through capillary action. The end grain absorbs 5 to 10 times more water than the face grain. When that concentrated moisture freezes, the ends split first. Once a crack initiates, each subsequent freeze-thaw cycle makes it longer. A crack that starts as 2 centimeters in year 1 becomes 20 centimeters in year 3 and runs the full length of the board in year 5. Medieval builders knew this. Their solution was not just about selecting better wood. It was about protecting the most vulnerable points before the wood ever faced winter. If this breakdown of the science behind why your deck is failing helped you understand what is really happening, hit that like button and subscribe. You are about to learn the medieval solution that actually works. Section 4. The lost Alpine treatment. No one uses anymore. The single most important step in Alpine wood preservation has been completely abandoned. Not because it does not work, because modern industrial processes cannot replicate it at scale. Alpine builders harvested resin from larch trees, not pine tar, not modern sealants. Larch pitch specifically. Larch pitch is resin collected by cutting shallow grooves in living larch bark. The tree exudes thick, sticky resin. This resin has unique properties. It remains slightly elastic even when hardened. It penetrates deeply into wood, and it is chemically identical to the resin already present in larch wood. The process worked like this. First, heat the larch pitch until it liquefies but does not burn. The temperature is critical, around 90 degrees Celsius. Second, apply multiple thin coats to the end grain of every board, not the faces, the vulnerable ends where water enters. Third, while the pitch is still warm, work it into the wood using stiff brushes. The goal is penetration, not a surface film. Fourth, allow each coat to cool and partially harden before applying the next. Medieval builders applied 3 to 5 coats over several days. The result is end grain that is sealed not just on the surface, but 5 to 10 millimeters deep. Water cannot enter. If water cannot enter, it cannot freeze. If it cannot freeze, it cannot split the wood. Modern deck builders might apply a coat of sealant with a roller, once on all surfaces. This does almost nothing for end grain protection. The end grain gets the same thin coat as the face, which is completely inadequate. After treatment, Alpine builders did something radical. They deliberately exposed the wood to a full winter before building anything permanent. Treated boards were stacked outside, fully exposed to weather for one complete freeze-thaw season. In spring, carpenters inspected every piece. Any board that showed cracking was rejected. Any piece with major checking went to interior use only. Only boards that survived with no damage earned approval for exterior structural use. This was quality control through natural testing. The wood had to prove it could handle Alpine winters before anyone trusted it in a building meant to last centuries. Modern construction uses wood straight from the lumberyard. No testing, no proving period. If a board fails, you replace it years later at significant cost. Medieval builders eliminated weak boards before construction began. Section 5. Why modern sealants cannot match medieval methods. Walk into any hardware store and you will find dozens of deck sealants, semi-transparent stains, solid stains, clear sealers, waterproofing compounds, all claiming superior protection. None of them work like larch pitch. Here is the fundamental difference. Modern sealants are film-forming. They sit on top of the wood. They create a barrier layer. When wood naturally expands and contracts with humidity and temperature changes, the film cracks. Once cracks form in the film, water enters. The protection fails. Larch pitch is penetrating. It soaks into the wood structure. It becomes part of the wood. When the wood expands, the pitch expands with it. When the wood contracts, the pitch contracts. There is no separate layer to crack. Second difference: chemical compatibility. Modern sealants are synthetic polymers. They are chemically different from wood. Over time, wood naturally degrades these foreign substances. The bond weakens. The sealant peels. Larch pitch is chemically similar to the lignin and resin already in larch wood. The wood does not recognize it as foreign. The bond is permanent. Third difference, depth of protection. A penetrating sealant might soak 3 mm deep. Larch pitch applied hot and worked in with brushes penetrates 8 to 10 mm. In a 38 mm board, that is a massive difference in protected zone. The trade-off is labour. Applying larch pitch correctly takes hours per board. Modern sealants take minutes. The industry optimised for speed. We lost durability. Section 6. The Alpine assembly technique that prevents splitting. Even perfect wood, perfectly treated, will fail if assembled wrong. Alpine builders understood that construction technique is the final piece of the durability puzzle. When you build a modern deck, you space boards about 3 mm apart. This spacing is for drainage. Water runs between boards instead of sitting on the surface. Alpine builders used gaps, but their reasoning was different. They calculated gaps based on expected wood movement. Larch expands and contracts with humidity changes. In alpine regions, humidity swings are extreme. A board might swell 2% wider in humid summer and shrink 2% in dry winter. For a 15 cm board, that is 3 mm of movement. If boards are installed tight together in summer, winter contraction creates no problem. But if boards are installed tight together in winter, summer expansion has nowhere to go. The boards press against each other. Internal stress builds. Something has to give. The wood cracks. Alpine carpenters installed boards with 3 to 5 mm gaps even in winter. This meant larger gaps in summer, but it also meant the wood could expand without stress, zero cracking from expansion pressure. Modern deck builders install to minimum gaps for aesthetic reasons. Tight boards look better, but they fail faster. Cut a board and look at the end grain. You will see curved lines, the tree's growth rings. These rings have a direction. One side was toward the bark, the other toward the tree's center. Alpine builders had a strict rule. Bark side always faces outward. Why? When wood shrinks and cracks form, they follow the growth rings. Cracks curve along the rings, not across them. If the bark side faces out and a crack forms, it curves away from the board's structural core. The crack stays near the surface. It does not propagate through the full thickness. If the bark side faces in, cracks curve inward. They travel deeper into the board. They compromise structural integrity faster. This seems like a small detail. Over decades and centuries, it is the difference between surface weathering and structural failure. Modern lumber mills do not sort by ring orientation. Boards come random. You get whatever the saw produced. Some boards are bark out, some bark in. Half of them are optimally oriented. Half are set up to fail faster. Alpine structures used wooden pegs, not metal nails or screws. This seems primitive. It is actually superior for freeze-thaw resistance. Metal and wood have different thermal expansion coefficients. When temperature drops from 20 degrees Celsius to minus 20 degrees Celsius, metal contracts more than wood. This creates a tiny gap around each nail or screw. Water enters this gap. The water freezes. The ice expands. The hole gets larger. After hundreds of freeze-thaw cycles, nail holes become loose. Boards start moving. Structural connections weaken. Wood pegs are the same material as the surrounding board. They expand and contract at the same rate. No differential movement. No gap formation. The joint stays tight for centuries. The disadvantage is installation complexity. Drilling precise holes and shaping matching pegs takes skill and time. Metal fasteners are faster. We traded longevity for speed. Section 7. The architectural design that protects wood, even the best wood. Treated perfectly and assembled correctly, needs architectural protection. Alpine buildings included design features specifically to minimize freeze-thaw damage. Traditional alpine structures have roof overhangs that extend 1 meter or more past the wall line. This is not aesthetic, it is functional. Deep overhangs keep snow and rain off vertical wood surfaces. Less moisture exposure means less water penetration. Less water penetration means less freeze-thaw damage. The math is simple. Modern architecture favors minimal overhangs, clean lines, contemporary aesthetics. The result is that rain hits your deck directly. Snow piles on horizontal surfaces. Maximum moisture exposure, maximum damage. Look closely at 800-year-old alpine buildings. and you will find carved channels in horizontal timbers. These channels guide water away from joints and connections. When snow melts, the water has to go somewhere. If it pulls against a joint, it will find a way into the wood. Carved drainage channels intercept that water and channel it to the edge where it drips free. Modern decking relies on gaps between boards for drainage. This works for surface water but does nothing for water that penetrates joints. No directed drainage, water follows random paths. Some of those paths go into the wood structure. Alpine builders never put wood directly on ground or stone. Every wooden structure sat on a raised foundation that lifted the lowest timber at least 30 centimeters above the soil. This prevented ground moisture from wicking into the wood. It allowed air circulation underneath. Dry wood survives. Damp wood fails. Many modern decks sit on concrete pads just a few centimeters above grade. Ground moisture stays high. The wood stays damp. Freeze-thaw damage accelerates. Section 8. How to apply this knowledge today. You cannot build exactly like a medieval Alpine carpenter. You probably do not have access to 3-year dried high-altitude larch or pure larch pitch, but you can apply the core principles. If you are building or replacing a deck, prioritize wood density. Ask your supplier for the hardness rating. Demand larch if possible, ideally with provenance information. If true Alpine larch is unavailable, Siberian larch is the closest equivalent with similar properties. If larch is not an option, choose the densest available softwood. Douglas fir is better than pine. Western red cedar is better than pressure-treated pine. The denser the wood, the better it will perform. Inspect growth rings. Look for tight, narrow rings. Avoid boards with wide spacing between rings. Wide rings mean fast growth. Fast growth means loose structure. Loose structure means failure. You cannot easily source pure larch pitch, but you can approximate the protection. Mix boiled linseed oil with pine rosin at a ratio of 3 parts, oil to 1 part rosin. Heat this mixture to 90 degrees Celsius. Apply it hot to all end grain using stiff brushes. Work it in. Apply 3 coats over 3 days. This will not last 800 years, but it will give you 50 to 100 years of protection instead of 5 to 10 years with standard sealant. For ongoing maintenance, reapply penetrating oil to end grain every 2 years. Do not wait for visible damage. Prevention is always cheaper than repair. When you install boards, pay attention to ring orientation. Yes, this takes extra time. It also doubles the life of your deck. Use wider gaps than standard, 5 mm instead of 3 mm. The aesthetic difference is minimal. The performance difference is major. If local codes allow, use wooden pegs or dowels for decorative elements. For structural connections where metal fasteners are required, use stainless steel only. Never use galvanized or coated steel. These will corrode. Stainless is more expensive but lasts. If you are planning a new deck, extend the roof overhang. Even an additional 30 centimeters makes a significant difference in how much rain directly hits the deck surface. Plan for drainage. Ensure the deck slopes slightly away from the house. 1 degree of slope is enough. Water must move off the surface, not pool. Keep the deck elevated. Minimum 30 centimeters clearance underneath. Ensure air can circulate freely below the deck. Even if you apply every principle perfectly, modern materials and modern climate will not give you 800 years. Medieval Alpine buildings used old-growth larch from virgin forests. That wood quality no longer exists in commercial supply. But you can absolutely achieve 50 to 100 year lifespan instead of 5 to 10. That is a 10 to 20 times improvement. That is decades without replacement. That is the difference between a deck that is a constant maintenance burden and a structure that outlasts your ownership of the home. The cost of forgotten knowledge. 800 years ago, Alpine carpenters understood material science we are only now rediscovering with modern instruments. They knew that altitude determined density, that winter harvest timing controlled moisture content, that resin crystallization required years, not weeks, that wood orientation affected crack propagation. They knew these things not through laboratory testing, but through generational knowledge, through buildings that succeeded and buildings that failed, through 800 years of observation and refinement. We replaced their system with industrial efficiency, fast-grown timber from low-altitude plantations, kiln drying in weeks instead of air drying for years, chemical surface treatments instead of deep resin penetration, metal fasteners instead of wood pegs. We optimized for production speed and cost reduction. We lost durability that measured in centuries. The science now proves medieval methods were not superstition. A 2021 study published in Construction and Building Materials confirmed that European larch from Alpine regions shows 64 to 80% higher freeze-thaw resistance than common softwoods. The mechanisms the study identified are exactly what Alpine builders selected for: higher density, higher resin content, tighter grain structure. Your deck cracks and splits in one winter, not because modern engineering is inadequate. It cracks because we abandon proven techniques in favor of cheaper, faster alternatives. We built an entire industry around wood that is biologically designed to fail. The medieval Alpine approach still works. High-altitude larch still outperforms lowland timber. Natural drying still produces stronger wood than kiln drying. Larch pitch still protects better than synthetic sealants. Wood pegs still maintain tighter joints than metal fasteners. The question is not whether these methods work. The question is whether we value durability enough to reject the industrial system that prioritizes speed over longevity. Next time you see a split deck board, remember that 800-year-old Alpine structures exist. The wood is still sound. The knowledge that built them is still valid. We just stopped using it.